Good afternoon, ladies and gentlemen. Our presentation now is on SOx, regulations and principles and economics of scrubbers. For a moment, I'd just like to present that first, Wärtsilä is known as a company that does a lot of engines of all sizes, from modest to quite high power ranges, the world's largest two-stroke to more handy-sized four-stroke engines across our portfolio. We also do a lot more than just engines. We also do everything from the automation on the bridge down and including the wet end of the propellers. Here you can see several different propeller designs for ships of all sizes, mechanical, propulsion seals, bearings, water jets, etc. But we also have automation, ship design, and many other features as well, including environmental management. In that area we have SCRs in several different vessels as well as on shore. Today we'll take a quick look at the environmental regulations, basics of scrubbers, we'll look at an installation case, the economics, and some conclusions behind this technology that allows vessels to employ higher sulfur fuels in the future with economic benefits and employing a scrubber. First, the environmental regulations. As we all know, the IMO was ratified into force in 2004. Now, with the progression of several tightening of the regulations, it's 2010 and now 11. But the first SICA came into being back in the North Sea and also in the Baltics. But we can see a progression of ever tighter sulfur requirements. If you look at the IMO, internationally, we originally started with Tier 1. Our four-stroke engines were well within that band. But that came into being in 2000. It was joined later in Tier 2 this January of 2011, which was a 20% reduction in the NOx requirement. Soon we have Tier 3 coming up in 2016, where NOx will drop a total of 80%. So this is the international requirement on NOx, and it's all based upon the RPM of the engine going out to higher RPMs on a negative log plot. Understanding the IMO, it's different for US EPA. It's based upon cylindrical displacement, different smaller categories with the larger engines, what you'd find in cruise ships today. So that's an important difference to keep in mind, is the difference between the US EPA and the international requirements on categorizing of engines. Here in the US, recently the EPA and US and Canada applied for an ECA to extend 200 miles off our coast, virtually encapsulating all of the US and Canada within a bubble. It requires vessels to use a very low sulfur fuel, effective 2012, August 1st, and in 2016 it becomes NOx. You can see that the older ones, the SICA, the sulfur emission control area for the Baltic and the North Sea, came into effect some years ago. They were targeting sulfur. An ECA is more broad. It covers sulfur and NOx. In the emissions control area, you can see the requirements tighten very rapidly to 0.1% in 2016, whereas the global requirement comes at a slower pace and it's not nearly as tight. 2012 is 35,000. We're already at 10,000, or 1% versus 3.5%. So in 2020, there'll be a decision point globally. Can they, in fact, meet the new requirements, or will it slightly slide out? And the 18 will be the decision point. But regardless of age, all ships must comply with the new sulfur requirements. So that means alternatives can also be employed, which implies scrubbers. Oscar just provided an chart that showed this change in the sulfur limit against the years in the SICA and the EU and ports, but notice dramatic reductions in sulfur over the years going ahead. Will the refineries have sufficient volumes of fuel available for our marine market space? Well, that requires them to invest billions in crackers and other devices to reduce the sulfur content in the fuels. Take a look at the SOx reduction methods of a scrubber, switch into MDO, or a full-time MDO. Green is good, yellow so-so, Red is not so good. A scrubber works with high sulfur, has savings, a payback. You avoid the use of multiple TBN lube oils. Fuel switching can be avoided, and additional tankage is not required. If you have to switch to MDO in the ECA, you've got a couple of so-sos and one not so good. Full-time with MDO, OPEX is very, very costly because of the champagne of the fuels. You also avoid, but additional tankage is required. So if you look at this scorecard, you can quickly see there's going to be a lot of interest in scrubbers for the cruise industry going forward. Here are the principles of scrubbers in short. What is SOx? It's the sulfur oxides. Dissolve in water, cause airborne acids. Basically, the way the scrubber works, the exhaust gas comes in, pass over a bed with water spray that scrubs it, and exhaust gas comes out. Into that water bed, you have water and NaOH sprayed, and the sulfides return out with the water. So basically, it's a simple cleaning basis, not unlike what you might have seen with an older ship, steamship, where we'd have a DC heater deaerating the air out of the steam. Here's a quick look at the entire system. Now what we're going to do, we're going to block off pieces of the system so you can focus on looking at very specific, simple parts of this. But basically, it's a closed loop. Seawater comes in to a heat exchanger, passes overboard, does not come into contact. All of the system otherwise is a closed loop with a holding tank and water treatment for the system. Zero discharge. As you know, that is going to be probably a very, very important criteria as ports continue to tighten their emission requirements. Another important thing is when you look at this whole system, there's only one small pump here and a metering pump over here. So the actual power requirement is very, very tiny in comparison to your entire ship on a closed loop system. So let's look first at only what the fresh water is doing. 1/10 of a cubic meter per megawatt hour is a very low water requirement. And with the advanced water treatment that's employed on cruise ships today, where you have gray water or other water, it may not cost you anything at all to have the fresh water come in. Why is the fresh water used? So it can help cool the process so you have less vaporization here and no light water plume coming up the stack. That's why it's done. But it depends on the ambient conditions, the seawater, and other things. But it's a very effective way to reduce your white plume. Let's look at the next part of this very simple system. Seawater enters in through a sea chest, a pump, to a heat exchanger, and back overboard. This is cooling the fresh water to minimize the entrapment of clean exhaust gases leaving the scrubber. So you have a plume, and it reduces the amount of freshwater consumption that we just talked about. It's fairly small. But it doesn't, in no way does it impact the sulfur removal efficiencies. So now we looked at two parts of that system. Let's look at a third part. The dosing. Alkali is dosed by an automatic process into the system. It provides basically at a 50-50 mix the sodium hydroxide or caustic soda need to help the reactions occur. It's dependent on the engine load and the amount of sulfur you're trying to attenuate in the fuel. Very small consumption level. Now we've almost concluded this simple system. The last part we're going to look at is the water treatment itself. Small amount of bleed off will pass over and come into this processing tank, exit and come over to the holding tank. Some sludge, as you would have for a purifier, goes into the sludge holding it. Here it is held and kept in a closed system for future discharge to a proper receiving facility ashore. So basically, these traces are retained in the sludge tank. The fluid is cleaned from the bed off, and the sludge impurities are placed for disposal ashore. So we've just taken you quickly through the entire system. in a very simple way. Seawater, freshwater makeup, the dosing unit. We learned about the scrubber in the beginning, and the holding sludge tank and holding tank for the scrubbed sulfur. It's a pretty simple and efficient, effective system that will find great applications in cruise ships as low sulfur fuel becomes more and more and more expensive. Let's take a look at an installation case. This is the motor tanker Sula, was approved by GL and DNV. This pilot was introduced and installed and operated for 2 years as an experimental basis. You can see it was situated outside the stack for convenience, and modularized and installed. Again, it used the same principle. Exhaust gas in through a water spray, a pack bed. You can see the exhaust coming in, coming back out. Very, very clear stack from startup to operation. You can see here a very, very tiny plume of white water vapor coming out. Another picture showing a very clean stack, and it was very well proven 2-year technology pilot. The actual test results for different engine loads and sulfur contents of 1.5 to 3.5% sulfur showed tremendous reductions in SO2, SOx, CO2, and the ratio. It was almost imperceptible the amount of SO2 that was resultant. So it worked quite well across a very broad range of operating conditions. Let's take a quick look at the economics. Depending on the vessel, her road profile, and equipment and other things on board, Wärtsilä can do a case analysis study for each and every vessel to help pick out precisely what is the right answer for that ship. But an important thing to look at is what is the differential you're looking at on marine gas oil, which is in red, and intermediate fuel oil, which would be in green or heavier in blue. Look at the spread. Very much approaching over $200 and sometimes as much as $700 a ton. Now there's an economic incentive to switch. So do you want to have the option, or do you want to be wedded into marine gas oil going forward? Well, a scrubber can give you a very fast payback as that spread expands and becomes larger. Oftentimes it can be approaching or near a year. Here's some of the economics. If you look at the fuel price differential, the operating savings versus the payback period, obviously the greater the spread, the faster the payback will become. It's expected to accelerate as it's believed that refineries have a difficult time getting sufficient sulfur low and ultra low sulfur fuels into the marketplace in the quantities required. So there's some real money back savings. In conclusion, scrubbers are fairly small in power demand. They reduce corrosion scaling, a little bit of bleed off, and basically are quite efficient when you look at a closed loop system. And closed loop is probably the best way to go forward when you look at all the sensitivities of the public and the ports for zero discharge. The competitive advantage gives you economics, great payback, compelling, and outside the ECA, you can still have benefits for those vessels that are trading internationally. They can go back to the international fuel, save money there. When they get into the ECA, switch on and go with the scrubber. So the real question is, can a cruise ship effectively avoid using a scrubber and economically do as well as her competitors who do? The key question comes down to money as a win and win on the environment. In the appendix, we've got some things to talk about how they can be set up in combinations, integration of scrubbers with boilers and multiple gen sets, what the consumption would be based on seawater temperature and loads of the engines, and some of the efficiencies based on sulfur content of the fuel and the amount of caustic soda to be consumed. Here you can see the efficiencies of multiple stages, and here is a plot that shows the extreme volatility in the price of the caustic soda. Obviously, that will impact the amount of payback depending on the vessel's load. Consumption is fairly linear depending on the operating power of the engine against the daily consumption rate.